welcome everybody. Just give me a minute here for technical difficulties. Can everybody see the screen over here, the modules?
Yeah, I can see it.
Yeah, okay. So you can see the module one. All right. Well, good. We are started then. So welcome everybody. This is module one, week one. It's an introduction to the course. And then we have two PowerPoints today covering chapters 1 and 2 of Schubert and Lebdia. Again, the class is Nursing 711, Scientific Foundations for Anesthesia. So hopefully you were in the right place. It says summer 2004 on here, not sure why. And that's me, and that's my email address. So first things first, just a big congratulations to you on your journey up to this point. You've been through nursing school, you've been in ICU, you've gone through the admission process. So just take a minute, take a deep breath. Be glad about where you are. So the picture on the left is just a hike, and I said, I'm sure right now you feel like you're at the bottom looking up to this giant stairwell. It's not an easy journey, but it's worth it. Just keep your eye on the finish line, one foot after the other, and before you know it, you'll be a CRNA. And then the picture on the right is me 10 years ago now, after I got my little exam and got my pass result. So it's possible, and anyone can do it. So I was always told the first slide is about the presenter, because obviously. So who am I? Why am I here? Just a little bit about myself. I graduated with my BSN in 2008. I got my DNP through Northeastern and the Army in 2015. I worked in the VA hospital system for till about November, October of last year. And then I kind of said, I don't like that work-life balance, that lifestyle. So now I work a little bit. I have my own company and just kind of do locums. I'm based in San Antonio, Texas. So locums around the area. I work in some ambulatory surgery centers, some large hospitals, just kind of whatever else I can get. I'm a father of two great kids who are having their last day of school today, so it's kind of sad. I also enjoy hiking, mountain biking, playing tennis, hockey, and reading. And then this is a modern picture of me at Sedona with my wife, kind of close to an edge there. So I always thought it was corny, but now that I'm faculty, I'm going to do it. So why don't we go and see if I can get you all back on camera here. But we can go around and just do kind of a brief introduction and maybe just a fun or boring fact about yourself. And we'll go in reverse alphabetical order. So Lauren Wilborn, you are first.
Okay, hi. I'm Lauren. I am originally from Chicago, but I grew up in New Baltimore, Michigan. I graduated my BSN at Oakland University in Rochester, Michigan, and then my experiences in the ICU at Mayo Clinic in the cardiac surgery heart and lung transplant in Rochester, Minnesota. A fun fact about myself is I am very scared about mass ventilating because I have really small hands. So that is like my biggest fear right now. So fun fact. Nice to meet everybody.
I will counter that, and I will tell you that my first boss at my first CRNA job in Nashville, she was like 4'11", 90 pounds, and she could mask ventilate and intubate anybody. So it's not about size; it's positioning and technique.
Thank you. That's very reassuring.
Yeah. Oh, and if you tell me your preferred name too, I go by not my full name, so I can call you the right thing. Mary Voigt, you're next. Is there a Mary Voigt? Okay. We'll move on to Justin Thomas.
Hi, my name's Justin. I grew up in the Toledo area. I graduated from the University of Toledo with my BSN, and I've been working at Toledo Hospital in the surgical ICU ever since. Um, yeah, pretty much. So, fun facts: I've been to 8 different countries other than the U.S.
Very cool. Welcome. Can we go back to Mary Voigt? I see her now. I see you hiding on page 3, Mary. Okay. Mic issues. Oh, okay. That's fine. We'll come back to you if you can. Good. If you can't, no big deal. Calvin Thatcher.
Hi, my name's Calvin. I graduated from Bowling Green State University through the University of Toledo nursing program. My ICU experience is in a medical ICU at Toledo Hospital. Fun fact. I don't really have anything off the top of my head this morning. Still just having my coffee, so. But
Fair
other
enough.
than that,
Well, welcome.
that's about all I got.
We have Angela Schlachter.
It's Schlachter, but you can just call me
Okay.
Angie. That's fine. My name is Angie. I used to work at surgical ICU at Toledo Hospital. I've also worked in adult ICU, outpatient surgery, pre-op and PACU at University of Michigan. A fun fact about me is that I am scuba certified and I love to scuba dive, but I hate to swim in the ocean.
Very cool. So you'll probably find once you start getting to anesthesia machines and all that, the pressures, and that's all, having a basic knowledge of scuba can only help you with that. Next is Catherine Salpe.
Hi, my camera's not working. I've been
Oh.
trying to figure it out,
That's fine.
but I'm here. My name's Catherine. I do go by Catherine. I've been a nurse for 4 years at Toledo Hospital in neuro ICU. I'm originally from the Akron, Ohio area, and then I moved to Toledo for my undergrad. And a fun fact is I'm deathly allergic to peanut butter, so I've never had it.
Welcome. Next up is Christine Recker Herman.
Good morning. I go by Chris. I'm actually an acute care nurse practitioner. I've been working in a smaller community hospital. Fun fact is I just got back from an amazing trip, Portugal.
Awesome. Well, it's good you were able to take a vacation before school started, so and kind of have some fun before the work begins. Next is Ryan Raymonde.
Hopefully this is working. Hi, I'm Ryan. I got my undergrad degree at Mercy College here in Toledo, and then I worked for as an ICU nurse at St. V's in the TICU, SICU, CV ICU for about 4 years. Fun fact, I like scuba diving, and before this, I was studying civil engineering.
Very cool. Welcome. Olivia Paduan.
Hello, my name's Olivia, but I go by Liv. I am originally from the Ann Arbor area, and then I got my BSN from University of Michigan. So after I graduated, had to move out a little bit, went to Chicago, and worked in their cardiac ICU. Fun fact about me, I think, I studied abroad in Tanzania, so that was pretty fun.
Very cool. Well, welcome. Next is Autumn Zymanski. Close.
Hi. It's Samansky, but it's actually Moreno now. I got married.
What is it now?
Moreno.
Moreno. Okay.
Yeah, it's slowly transitioning.
Yeah. Slowly transitions over. Well, congratulations.
Thank you. I am from Bedford, Michigan, so I'm local to like the Sylvania, Toledo area. I got my undergraduate at Mercy College, and then I've worked in the medical ICU at Toledo Hospital for like close to 4 years. The only fun fact I can think of right now is I have a Persian cat named Meatloaf.
That's a good fact. I got a cat running around here somewhere that'll probably show up halfway through and see what's going on. So that's okay. Next up is Fina Colts.
Hello, my name is Faina. I prefer to go by Faina, but if you can't pronounce it, you can say Faye. I've been a nurse for 5 years. I did a mix of medical, surgical, trauma, ICU, but the last 3 years were medical ICU. Fun fact about me is I'm a first generation American and I speak Russian fluently.
Cool. Well, welcome. Next is Phoebe Kaler.
Hi, I hope you can hear me okay. My name is Phoebe Taylor, and I have experience in a surgical trauma ICU at ProMedica Toledo Hospital, and I graduated from the University of Toledo. A fun fact about me is that I am an identical twin. She's also a nurse, and she's stationed in the Air Force, and she's actually stationed in San Antonio, Texas. So in Texas, just like you.
Woohoo! Good. She should go to CRNA school through the Air Force. Right. Welcome.
Yeah, I think so.
The next one is, I'm sorry, you got to help me with this one. Last name is Jaffer. How do you say your first name?
Sohaib.
Sohaib?
Yep.
Okay.
Hello, everyone. I'm Sohaib. I was in a traditional BSN. My BSN was actually in psychology. So I did a master's entry into nursing in Baltimore at Johns Hopkins University, the 2-year program. I moved back and started working for Henry Ford, where I worked in a combined neurosurgical and trauma ICU for about 3 years. Before getting my MSN, I actually worked in EMS for 3 years, where it piqued my interest and went into nursing. An interesting fact about me is I've been skydiving before, and I have 2 kids.
Oh, cool. Welcome. Next is it Juan who?
I'll help you out here.
Yeah.
My name is Xuan Hao.
Xuan.
Last name is Hao. Yes. You can. I go by Xuan. I tell people who know science to think of my name as Xuan in Xuan cells.
Yeah.
Okay. I'm from Beijing, China. I came to the States 8 years ago to study nursing. I graduated from Oakland University. My experience includes medical ICU in California, Fresno, California, and cardiac ICU in downtown Henry Ford. And a little boring. I will talk about boring facts about myself. I'm just lack of the humor gene. I always complain about it to my parents. I just don't have that trait in me. I'm a dead serious person. I'm still slowly picking up here and there about the American culture and the humor part of it. I have a super delayed response. When you strike a joke and I would just be awkwardly smiling and not understanding it. That's me.
Very cool. Welcome. Caitlin Fandre.
Hi, everyone. I'm Caitlin. I go by Caitlin. I've been a nurse for 5 years. Mainly my time is spent at Toledo Hospital and Cleveland Clinic and various ICUs. And I made chocolate chip banana bread yesterday, and it's awesome.
All right, that is a good fact. Lara Fakirdi. How do you say your last name, Lara? I won't butcher it.
It's Backerdine.
Backerdine. Okay.
Yeah, it's okay. Yeah, good morning, everyone. My name is Laura. I've been a nurse for 3.5 half years. I primarily worked on a CV slash surgical unit. I'm going to copy Phoebe a little bit with my fun fact, but I also have a twin sister who's a nurse. She works on a neurotrauma ICU, and she's going back to school to become a perfusionist.
Very cool. Next is Laura Dijak.
Yep, that's how you say it. Good morning. I'm Laura. I live in Jackson, Michigan. I went to Ferris State University, which, if I use my hand, it's a little north of Grand Rapids, but I live more down here, closer to Lourdes. Been a nurse for 12 years. I primarily work ER, but of course I worked ICU, dabbled in some other things. Fun fact, as I stare out my window here, I did not find any morel mushrooms this year, which made me really sad. They're delicious, and sometimes I find a bunch, and some years I find none.
Anthony Duvendak.
Yeah, hey, my name is Anthony Duvendak. It's hard to pronounce sometimes, the last name. So I am originally from the Fort Wayne, Indiana area. Went to school in Mishawaka, Indiana at Bethel College. Moved south to Alabama to work at UAB in the surgical ICU, and then now I moved back here to Sylvania, Ohio. Fun fact. Well, I guess recently my wife and I just went to the Tulip Festival in Holland, Michigan. It's fantastic if anyone ever wants to go, or if anyone has been. Yeah, super beautiful.
Very cool. Welcome. Next is Jonah Childress.
Hey, good morning. My name is Jonah. I graduated from Bowling Green State University. Been working at St. B's cardiovascular and trauma ICU. Fun facts, not so fun fact, I am in the Army Reserves.
Very cool. Welcome. Christopher Campo.
Hi, Chris Campo here. Originally from Windsor, Ontario, Canada. Received my bachelor's from Windsor. Later went back and got my master's. I've only actually worked as a nurse in the States at Henry Ford Hospital. My critical care includes ER and medical ICU. And fun facts, I've climbed Mount Kilimanjaro in Africa before.
Welcome. My condolences to the Maple Leafs on their choke in Game 7. Michaela Burks.
I don't know. Can you hear me?
Yes.
Okay, perfect. Okay. My name is Michaela. I go by Kayla. I am originally from Tiffin area of Ohio, very small town near it. I went to UT for my undergrad, and then I've worked at St. B's in the surgical trauma cardiovascular ICU for about 3 years. And a fun fact about me is I used to show cows at the fair, like in 4-H.
Very cool. Welcome. Alexa Bonfaz.
Hi, my name's Alexa. I go by Lexi. I have been a nurse for 4 years. I am from a little town called Bluffton, Ohio. If you know where Findlay is, it's like 15-20 minutes south of Findlay. I got an associate's degree initially at Rhodes State College in Lima, and then I did my bachelor's online through University of Cincinnati. I worked at a hospital. I worked at a hospital in Lima, the same hospital as Chris, actually, and then went to travel at Toledo and did travel and staff there for about 2 years. Fun fact about me, I'm the second oldest of 7 kids, and the youngest of us is 13. So I basically kind of raised her. So, yeah.
Well, welcome. All right. Last but not least, Sydney Alexander.
Hi guys, my name is Sydney. I go by Sid or Sydney. I'm from Port Clinton, Ohio. I graduated with my BSN from Bowling Green State University. I started in the ER and then transitioned to the medical ICU at Toledo Hospital. So I've been a nurse in total for about a little over 5 years. I know we have a few twins here, sets of twins here. I do have a twin brother, so that's my fun fact.
I think 3 sets of twins total so far. Okay. Very cool. They should all go to CRNA school, and then you guys can all work in the same hospital. All right. So I think Mary, is your thing working, or do you want to just skip it? Your mic, I know you have mic issues. Okay, that's all right. We can skip it and keep going. Well, welcome. All right. So let's see if I can get back to screen sharing mode here. Can you all see the PowerPoints?
Yep.
Yep. Okay.
Yeah, I can see him.
Perfect.
I can't see the PowerPoint. I don't know what's going on, but if there's something I can do, or if I can come back, or
let me see. Everybody can, but Calvin.
Yeah.
Okay.
I
Yeah,
do
maybe.
have it pulled up, so it's not a big deal.
Yeah, maybe if you want to exit and come back, you can, or whatever you want to.
I'll try that once, and
I think it's just a you issue. Sorry.
okay. No big deal.
I'm just kidding. So everybody can see this?
Yep.
No. Okay. All right.
Yep.
So about this class. So it's nursing 711. It's scientific foundations for anesthesia. This course is going to focus on chemical, biochemical, and physics that are pertinent to human physiology, pharmacology, and biomedical equipment. Basically, we want to give you a good, solid science foundation for all the awesome anesthesia stuff you're going to learn later. Let me see. I think that's Calvin trying to get back in. See if I can let him back in. Okay. All right. Calvin is back in.
I see it now.
Sweet. Yeah, so it's basically structured. We'll examine physics, some general and organic chem, biochem, and they're mainly the clinical correlations, specific things like measurements, chemical and physical properties, molecular structures, fluids, energy, bonding, gas laws, and solutions. So again, I know a lot of you all seem like you're pretty close to the formal schooling. It should be kind of a review of hopefully what you learned in chemistry class and physics class. If not, we'll give you everything you need to know to again give you a solid foundation for what's coming ahead. So how is it set up? They're weekly PowerPoints. I'll try to post them on Canvas on Sunday. And then there's a corresponding chapter of the book as well, Chemistry and Physics for Nurse Anesthesia by Schubert and Lebdia. I said in-person lecture presentations on Thursday. The last time I checked, I know I sent out that group, that not GoFundMe, SurveyMonkey about it. So if you haven't responded to that, please respond. Basically how my work schedule goes is that I have Thursdays blocked off through June. If we want to do classes during the daytime, it'd have to be on Thursday through June. If we want to do it in the evening after about 5 o'clock your time, I'm pretty much free whenever. So we can do that. I'll probably send another survey out before I do my July schedule just to make sure that, the Thursdays or whatever day we want is the day y'all want to do it. I'm here for you, so whatever we can work out, we will. There are 4 tests. So far, these are the days on Thursdays. I'm kicking around doing just an optional quick test review on the Tuesday before, mainly just if you have any questions or something doesn't make sense, you can just kind of pop in and listen. I do plan on recording and posting these lectures. So if you have a doctor's appointment, if something happens, I get it. I mean, you're adults. This is grad school, so it'll be recorded. You'll have the PowerPoints in the book. There will be one final group presentation, groups of 4 to 5. There's going to be a little bit more on that to come. Basically, I want you guys getting familiar with working as a group, standing up and presenting. These are all skills that are going to help you later come graduate school time when you're talking to your staff or giving a report or presenting your DNP stuff. This is the grading scale set by Lourdes University. I would also encourage you to review your handbook as well. It's a 10-point scale, so anything above a 90 is an A, anything above 80 is a B, anything below that is, I think, unsatisfactory. There are 4 exams worth 24%, and then the group project at the end is worth 4%. Also, if you have additional questions, please see the syllabus that's posted online, and it was attached as the first email. You can also refer to your handbook for additional information. The syllabus is on Canvas, and then I will work on at least uploading the course content is in the syllabus, but I made a calendar that I can upload as well if you prefer the more visual. So the bibliography, Schubert and Lebdia, the 3rd edition is preferred. I think I used the 2nd edition when I was in school, and it's basically the same thing. So if you have a 2nd edition, you should just be able to read the content and then, whatever chapter is about, and just kind of find the corresponding content in the 2nd edition. Does anyone have any questions about the syllabus or any of that before we launch into it? And the chat is active, so if anybody, doesn't want to raise their hand and talk out loud, you can put it in the chat and it'll pop up and see it. Oh, I will also say that this lecture is being recorded and then transcribed, so I will figure out how to. The test format will be a good question. It's going to be multiple choice. There may be some written, not written, but fill in the blank math questions, but no essays or anything like that. I'm limited by what Canvas can make.
Will the tests be proctored, like if we have to download like a lockdown browser?
Yeah,
or is
there's
it-
lockdown browser in Canvas. And so it'll be, it should be the same time we decide on for classes. You'll just log in. I believe I give you like a password, and then you get into the test from there and take the test.
Thank you.
I do have a question.
Yes.
Obviously, there's in this first PowerPoint, there's a lot of like formulas and stuff. How much like time should we put into like memorizing those, I guess?
Not much. I'll try my best to provide you with everything you need. I know if you looked at it, there's some like drug calculations and stuff. You don't need to memorize, the dose of propofol yet. If there's any calculations, I'll give you what the mg per kg dose is. But again, it's for anesthesia. It's not for chemistry, so we want a basic overview of it.
All right, thank you.
Hi, Dr. O. So regarding the online review, would that be just like this? Log on to Teams as
Probably probably just like this.
Okay, sounds good. Thanks.
Very good questions.
Yeah, I guess quick question. So
Yeah.
since we're recording this, where can we find this recording if you want to go back in Canvas?
That is a good question. I do not know. I will have to figure out where to post it.
That's fine. That's fine.
It may be question. The Teams link might still be available, so we might be able to just leave it up on Teams, and then you can come back to it on Teams. But that is a good question. I'll have to look into that. Any other questions before we move on to chapter 1? Going twice. Right. So chapter 1 is measurement. And so the big question is, well, why does this matter? What's this got to do with the CRNA? You'll see this quite a bit, but from the I say from the bedside to you. So you determine a drug dose or measure a base deficit. If you're doing calculations and you come across something that says, that just doesn't seem right, your calculated dose is lower or higher than you anticipate. Just kind of a tip in the, when you're in the clinical is if you got to recheck your calculations, if you have to give more than one vial of something, you should probably recheck your calculations. The example Schubert and Lebdia gives is most medications are packaged in common doses, like spinal bupivacaine comes as 7.5% in 2 mLs. So if you do your calculations and you have to draw, 2.9 cc's, you might want to double check to see does that seem right or not. Spinals are based on height, so if you have Yao Ming or a 7-foot tall basketball player, that would be correct. But if you have like a 5'4" person and you give them 3 cc's of spinal bupivacaine, you're going to have a rough day in clinical. So the idea would be know the drug calculations, know how to use them. So in this lecture, we'll go through some basic math, just a little bit of algebra, square roots and squares, logs and anti-logs, exponents, scientific notation, measurement and significant figures, the metric system, conversion factors, and then we'll go with some math calculations for the CRNA, and then density and specific gravity as well. So your basic math review, if you remember this from early on, there's the order of operations. The acronym is PEMDAS, so how you do things. Parentheses go first, exponents go next, multiplication, division, addition, and a subtraction. If you've got a mnemonic to remember it, that's good for you. For some reason, I remember please excuse my dear Aunt Sally from like 4th grade math. So how is this important? You can look at our equation here. You could have a different answer depending on how you do the order of operations. Technically supposed to do 4 plus 2 is parentheses, and then multiplication, and then work it out from there. Again, this probably won't really be on the test just because it's basic math, but it's important for you to know and review the order of operations. We can move on to algebra. Just a reminder that addition and subtraction are inverse operators of each other, so are multiplication and division. Usually a problem will involve solving an equation for a variable. So you want to convert the equation into x, or solve for x. If you want to isolate a variable, you need to undo any operations that are tying up the variable by applying the inverse operation. So if it's multiplication, do division. If it's division, do multiplication, etc. Again, the point of this would be to think of it more as a ratio. That's going to come in handy later when you learn about gas laws and when you're calculating gas laws and stuff. So again, very basic math here, but 12x equals 180. What's x? It's multiplication, so you do division by both sides and you get your answer. Okay, sounds great, but let's give an anesthesia example. So it is CRNA school. So if you look at Charles's law, which describe the effects of temperature on the volume of gas, which we'll go into great detail in a couple lectures, but the ratio is volume 1 over temperature 1 equals volume 2 over temperature 2. So if you have the volume and temperature of a substance or a gas at a certain oxygen at a certain temperature, and you want to know how much oxygen there is at a different temperature, you can use this equation to calculate it out. So this is going to come up again in pharmacology in your inhalational anesthesia lectures. So don't memorize Charles' law yet, but just know that it's a portion, it's a ratio. To do one thing on one side, you have to do it on the other side. So if you wanted to solve for T2 over here, you can cross manipulate the equation and cross multiply it. So again, the big point here is they're they're proportional. So as temperature goes up, the volume goes up. The temperature goes down, the volume goes down. If you think about in fall, the first time you go outside and it's, you know, one of those really cold fall mornings and your tires on your car are low, that's because the temperature is down, so the volume goes down. And then just a brief overview, basically what I said, addition and subtraction to the inverse, multiplication, division to the inverse. Sorry, I got a yard guy who's blowing leaves outside of, right outside the window right now. Can everyone still hear me with the background noise?
Yeah, I can't hear the leaf blower at all.
Okay, okay. All right. And then the example here we have is converts Fahrenheit to Celsius. Again, don't memorize this formula, but you know, if you need to do it, a lot of the things you'll do, you'll get in, you know, Celsius temperature and then just a quick conversion of Fahrenheit. So Fahrenheit 9/5 times degrees Celsius time plus 32. So to solve for this equation, just remove the additional item 32, the multiplication factor 9, the division factor 5. And just remember, since 5 is below the division or fraction bar, it's included in the equation by a division operation. You have to start with clearing the additional operation. So they did, you know, so minus 32 here gives you, you know, Fahrenheit minus 32 times 9/5 centigrade. Now the centigrade is multiplied by 9 and divided by 5. So do the opposite to inverse, so that clears it off. That gives you your answer. Another option, another thing you'll need is calculating body mass index. It's kilograms, meters squared, and usually you have to convert pounds to kilograms and heights to inches, heights and inches to meters. So an example of this would be calculate the BMI for a 68-inch, 165-pound male. So first you convert your pounds to kilograms. So 165 divided by 2.2 is 75 kilograms. You convert inches to centimeters to meters squared. So 68 inches times 2.54. And then the square root of that over 100 is 2.98 meters. And then divide kilograms by meters squared. And you get a lovely BMI of 25.1. I don't know in Ohio, but that is a rarity in South Texas. The next thing we talk about is square roots and squares. Just as a reminder, they're also the inverse of each other. So you can use them to cancel each other out in the equation. So square root of x plus 6 equals 60. You can just square that whole thing and make it 6x plus 6 equals 100 because 10 squared is 100. And then subtract 6 and you get your answer, 94. Maybe a newer concept, maybe not. The logarithms, they're functions used in a lot of things like pH is probably where you know them for AVGs, the Richter scale of earthquakes. They're mixed up exponents. So basically, you know, I'm sure you know 10 squared is 100. So 10 is the base and 2 is the power, and then 100 is a result. So it's not a number, but part of a number like an exponent. So in other words, you need 2 factors of 10 to get to 100, 3 factors of 10 to reach 1,000, and so on. So a logarithm is just another way to express this exponential expression. So the log expression for 2 squared is 100. So 10 log equals 2. So if you think about, basically it's 10 times worse each, you know, so if your pH is 7, if it goes down to 6, it's only one pH, but it's quite a bit worse. And we'll get into that more in acid base. Or if you think about, oh, is a 6.0 earthquake, a 7.0 earthquake is, a step higher. Yeah. So 10 is the base of the logarithm, and then 2 tells us what we need the factors. We need 2 factors of 10 to reach 100. But so that's the simple explanation. It can get harder if you want the log of a number, not the integral power of 10. So if you have a number like 110. So again, you use your calculator. I know in the olden days they had log tables that you had to memorize, but you don't have to do that anymore. So your calculator, even your at-home calculator and your Apple calculator has a log button and a 10x button. And just as a reminder, the log and the anti-log operators are inverse of each other. So if you take the log of a number and then the anti-log, you'll get the original number.
So we won't need like a special calculator for this class.
No, you can, yeah. And I'll double check to make sure Lockdown Browser has, you can access the calculator. Usually you can, so you can use basically your scientific calculator here that's available on your PC if you have one. If not, I think you could probably just use a regular calculator, whatever calculator you have at home. So the example, if you take the log of 110, you get 2.014. And then if you take 10x of that, so log, and then 10x is anti-log, and then you'll get back to your original number. There's just a couple of handy rules. The logarithm of any number between 1 and 10 is always 0 plus a decimal. The logarithm of any number between 10 and 100 is always 1 plus a decimal, which is greater than 1 but less than 2. And then the logarithm of any number between 100 and 1,000 is always 2 plus a decimal, which is greater than 2 but less than 3. So we can move on to exponents. They are shorthand for the number of times a quantity is multiplied. You'll most commonly encounter them when using scientific notation. So 1 cubic centimeter is 1 times 1 times 1, centimeter times centimeter, or 1 centimeter cubed. There are some special cases. Any quantity except 0 raised to the 0 power equals 1. So 5 to the 0 power is 1, centimeters to the 0 power is 1. Any quantity to the negative 1 power is equal to the reciprocal of the quantity. So 2 to the minus 1 equals the reciprocal of that, which is 1/2. Moving a quantity across a division bar changes the sign of the exponent. That's true for numbers and variables. So grams to centimeters, we move it across, it's grams to centimeters to the -3. And then this is 2 to the -1. Now it's from the opposite to the positive. There are also some special cases. When powers are multiplied, the exponents are added. So 2 squared plus 10 to the 4th is 10 to the 6th, because 4 plus 2 is 6. When powers are divided, the exponents are subtracted. So centimeters cubed divided by centimeters to the first power is centimeters squared. Move on to scientific notation. Using exponents, powers of 10 for handling very large or very small numbers. A number in scientific notation consists of a number multiplied by a power of 10. The number is called the mantissa. Only one digit in the mantissa is to the left of the decimal place. The order of magnitude is expressed as a power of 10 and indicates how many places you had to move the decimal point so that only one digit remains to the left of the decimal point. So 6.02 times 10 to the 23rd, Avogadro's number, that's what it is written out. So if you move the decimal point to the left, the exponent is positive. If you move the decimal point to the right, the exponent is negative. 10, 1.054, 10 to the minus fifth. It's negative, so you basically just move it to the left. 1, 2, 3, 4, 5, and you get your number. Larger numbers greater than 1 have positive exponents when expressed in scientific notation. Smaller numbers less than 1 have negative exponents. Basically, virtually all scientific calculators have an EE key or an exponent key that it's used for scientific notation. So in order to calculate it out, step 1 is on your calculator here, you have exponent. So enter the mantissa, press exponent, and then enter the exponent, changing the sign if necessary. So 5.1 exponent, it would make it 10 to the fifth equals 510,000. So why don't we take, so we're at 50 minutes right now. Why don't we take like a 10-minute break, just to stretch, walk around a little bit, get a drink of water, and then we'll come back with measurements and significant figures. I will start a timer. Do you need to know Avogadro's number? Yes, you do. Good question. I'm going to turn off the mic and we'll come back in 10 minutes. So stretch, get some coffee, do what you need to do. We're going to start back in 1 minute. Start filtering back in virtually. We are going to move on to measurements and significant figures. So measurements and significant figures, scientific conclusions can't be more reliable than the least reliable measurement. One tool to assess the reliability of a measurement is the number of digits that are reported. Significant figures are digits in a measured value that have a physical meaning and can be reproducibly determined. Only applies to measured quantities, which always have some inherent uncertainty. Numbers not obtained using measurement devices are called exact numbers. So we talk about, being precise with your measurements, and this is the way that scientists do that. So just a couple rules. Non-zero digits are always significant. Captive zeros, which is a zero between non-digit zeros, are always significant. So I'm trying to find a captive zero here. Leading zeros at the beginning of a number and located to the left of a non-zero digit are never significant. So this would be a leading zero here. Trailing zeros at the end of a number and located to the right of a non-zero digit are only significant when the number contains a decimal point. So if you look at our little numbers here, there's a decimal point. So this zero is significant. These zeros are significant, and then this would be a captive zero. But this only has one significant digit because the zeros preceding are not significant. And then this only has one because there's no decimal point. It's just these two zeros in the 200. The result of a calculation cannot be more reliable than all of the measurements which the calculation is based. So basically the rules here are when adding or subtracting, keep the smaller number of decimal places. When dividing or multiplying, keep the smaller number of significant figures. So apply these rules according to the algebraic hierarchy of calculations, PEMDAS, that we talked about in the first couple slides. So this example here, you're adding, this has 1, 2, 4 significant digits, and then 4, so your answer is going to have 4. But when you multiply, this number only has 3 significant figures, so your answer only has 3 significant figures.
Are you able to use like a pointer for the slides? I don't think I'm seeing like.
Oh, you're not seeing my arrow?
Yeah, I don't think I see it. Thank you.
Yeah. Is that there we go. Yeah, thank you. So basically I said when you multiply, this number has 3 significant figures, so then your answer can only have 3 significant figures. So the other thing we talk about is accuracy and precision. So accuracy is the agreement between experimental data and the true value, and precision is the agreement between replicate measurements. So accuracy, it's accurate and precise, you get the same thing every single time. Not accurate, but it's precise, you get repeatable answers, but it's way off target here. Accurate but not precise, you're still getting within the middle, but the numbers are pretty different. And then not accurate, not precise, everything is, all your answers are all, numbers are kind of all around. So we can move on to the metric system. So hopefully you are briefly familiar with that. Basically, it's a logical system, so it makes sense. There's base units, there's multipliers, there's meters, kilograms, all the numbers, and then your prefixes here. Again, don't memorize this. Just be aware of it. The system makes sense, unlike the imperial system, so it's easy to convert between meters and kilometers and milliliters and centimeters and everything. So, what you should be familiar with, and hopefully you are by now, is some basic conversions. An inch is 2.4 centimeters. A mile is 1,600 kilometers. And a mile is 5,280 feet. And then you can look at these as well, the pounds to kilograms, kilograms to pounds, and then your volume conversions as well. Again, not to memorize. If there's any calculations on the test, I'll give you these formulas. The point isn't to just memorize some figures. The point is to be able to do the math quickly and do the math accurately as an anesthesia provider. And then I just thought this was funny, is that there's two kind of countries, those who use the metric system and those who have landed on the moon, which I guess other countries have put probes on the moon. So it's not entirely true, but we put people on the moon. Allegedly. Just kidding. So then conversions. If you have an inch, it's 2.54 centimeters. So how many inches are 35 centimeters? Again, 35. Oh, sorry. Clicker here. So 35 centimeters, you have 35 centimeters divided by 2.54, that gives you 13 inches. So this brings us to the more relevant to anesthesia and more relevant to CRNA school. A lot of that was hopefully a review of your chemistry and your basic physics and just basic stuff you've done as a nurse. We'll move on. Again, the point isn't to master this information. The point is to be able to, it's only going to come in handy later as you get to simulation, you get to clinical. So when I took this class many years ago, this is what one of our professors said. He said, you'll need to do this 5 to 6 times a case, 600 to 800 cases a year. Hopefully you're practicing for 20 to 35 years. So 75,000 to 144,000 times in your life. You'll need to do this. Very basic stuff. I'm sure you'll have to have care plans when you start in the clinical, and you'll do calculations. The patient is this number of kilograms. Here's my induction meds. Hopefully you do that as part of your simulation as well. So hopefully we're shifting from what you knew to hopefully some new stuff here. Again, someone asked this about, I think someone asked the question about referencing the doses and stuff prior to starting. For test purposes, I want you to be able to do the math. I don't care about memorizing doses because that's not within the scope of the course. So if there's math questions on the test about propofol or fentanyl or whatever else, I'll give you the conversions I want you to use. So something you've probably come across and something you definitely will, percent solutions, converting percentages to milligrams per milliliter. And again, a percent by definition equates to grams per 100 cc's. So sodium chloride is 10% solution. So by that definition, it's 10 grams per 100 mLs. So your good anesthesia percent bupivacaine, which is a local anesthetic, it's applied at 0.5% solution. So that means it's 0.5 grams per 100 milliliters, which you can convert out to 5 milligrams per milliliter. And that basically you convert grams to milligrams. There's 1,000 milligrams in a gram. So you just multiply by that and you get your number. Sorry, multiply by 1,000, and then that'll give you your answer over 100, and then divide by 100 to get your grams per ml. Our next example is lidocaine, which is a 2% solution. So that's 2 grams per 100 milliliters. Again, pretty easy calculation, but 2 grams, convert it into milligrams, multiply by 1,000, and then divide that by 100, and you'll get your 20 milligrams per ml dose. So if you say, Dr. O, I need an easy solution. I need to do this fast. I hear you. All you have to do is just move the decimal one place to the right. So 10% solution is going to be 100 milligrams per milliliter. 0.5% is going to be 5 milligrams per milliliter. 20%, 2% is going to be 20 milligrams per milliliter. And if it's 2.7625%, that's going to be 27.5. This will come in handy. The example I can give you is if you're doing a block, you're worried about the max dose of local anesthesia they can get, and that's based on a kilogram. So if you have 5% ropivacaine and the patient's, you want to know, and then your max dose is going to be something like 400 milligrams. You want to know how many cc's you can give them, and you can easily calculate that number out to make sure you're below the threshold that would be dangerous to them. Again, not on the test, but just a way to remember it, connect it to, hey, you're actually going to use this. Then we can move on to concentrations expressed as ratios. And it's similar, but it's 1 gram per the number of milliliters specified. So 1 to 200,000 means 1 gram and 200,000 milliliters. This would be like your little epi syringe over here, your epi vial you dilute down. So in order to calculate that out, it's 1 over 200,000. You want to convert down to micrograms per milliliter. So 1 gram is 1,000 milligrams. And then that will give you milligrams, and there's 1,000 micrograms. And then you divide that by 200,000, and you get 5 mics per ml.
I have a question.
Yes.
That symbol for 5 micrograms, I'm used to not using that symbol. Would you
The
prefer
UG?
right? Yeah.
Either one works.
Okay. Thank you.
Yeah, MCG or UG. I think this is the Greek number for it. And then sorry. So this is the epi. So epi, I don't know if you've seen these. I'm sure if you work in the CVICU, you've seen. I don't know if you'll have the vials, but it's 1 per 100,000, so a little bit stronger concentration. So it's 1 gram. 1 gram per 1,000 milliliters. In order to convert that over, you have to multiply by 1,000 because there's 1,000 milligrams in a gram, and divide. So you get 1 milligram per ml. So more concentrated. And then more concentrations. 1 gram per number of ml specified. So 1 in 10,000 means 1 gram in 10,000. So I know this is a little repetitive, but it's just push home. Each concentration is going to be its own equation. So if you know the principles behind it, you can just plug it in the numbers and get your answer. So if you have 1 gram, you can multiply it by 1,000 for 1,000 milligrams. And then it's 1 in 10,000 means you have to divide by 10,000 to get per ml. So 0.1 milligrams per ml. And then there's a ratio proportion. You probably remembered this, hopefully from your nursing days. Your desired dose over dose on hand is how I learned it in school. The dose is usually per kilogram. There's 2 methods to solve the problem. You have the available proportion to desire, and then over the dose on hand. So you may have seen this as DD over DOH, whatever you want to call it. Desired over available times quantity equals X. So if you have 10 milligrams in 1 ml and you want 120 milligrams, you can write it out like that equation. then basically multiply it out. So you get cross multiply like that, and then cross it out, and you'll get X equals 120 milligrams, and then divide that, you get 12 mLs. So that is good in theory, but what about in practice? Oh, good question. So the next question, some doses for common anesthetic drugs you're going to give. Again, don't memorize the doses, just memorize the ideas behind it. I'll give you, if there's an induction dose or a dose I want you to use, I'll give you that. Just as a reminder, 1 kilogram is 2.2 pounds. For this case, the induction dose of propofol is 2 mg per kilogram. So if your patient's 187 pounds, how many kilograms is that? And what is your dose of propofol? So the first thing we're going to do is do kilograms to pounds. 100, that should be pounds, so sorry. 187 pounds divided by 2.2 is 85 kilograms. So we know our patient is 85 kilograms, and then we multiply that by 2, because it's 2 mg per kilogram. 170 milligrams of propofol to put this patient to sleep. But then we have to take it one step further, because there's no, how do you give 170 milligrams? Who knows? What is that in cc's? So you have your desired dose, which is 170 milligrams divided by your dose on hand. You can memorize, or you can look at the bottle, which is 10 milligrams per ml. And going back to your fibrates, you should always double check your concentrations and double check your drugs before you give it. It does sometimes come in different concentrations, and each facility you work at may have their carts stocked differently, and the vials may look different. So always double check. The last thing you want to do is grab something you think is one drug, push it as if it were that drug, and then find out, oop, it's something else. So 10 milligrams per milligram is your dose on hand. 170 milligrams is your desired dose. You can divide, and that gives you 17 milliliters, which is 17 cc's. So congratulations, you've induced your patient. The next step, you want to give them some fentanyl. And for this purposes, we want to give 3 mics per kilogram patient for an induction dose. I changed the weight of the patient just to give you another example. So there's 65 kilograms. So again, 65 times 3 is 195 mics. But again, 195 mics isn't on your syringe, so you want to figure out how many cc's you're going to give. So you have your dose over here, 50 mics per ml. And then you want 195 mics, so desired dose divided by dose on hand. It's set up like this, but the cross multiply. But that gives you 3.9 mLs. Because 195 divided by 50 equals 3.9. So now we've given propofol, we've given fentanyl. We're going to say we can mask ventilate him or her. So now we want to give some rocuronium. We'll do one more here. So last one. Let's give our non-RSI dose of rocuronium, which for this purposes is 0.6 mg per kilogram. Your patient still is 65 kilograms. So how much rocuronium is that? So 65 times 0.6 mg per kilogram. You can also, just to make it easy. So that gives you 39 milligrams. And again, to figure out, we have our desired dose. We have our dose on hand, 10 milligrams per ml on our vial here. So again, easy. You can divide by 10, or you can just move the decimal point 1 point to the left, which will give you 4 milliliters, 3.9 milliliters, which is 4. So just for reference, I did 13 cases yesterday at my urology surgery center. So I did this same thing 13 times in my head very quickly. So it's stuff to know. It's stuff that'll come in handy come simulation time and come clinical time.
Question for the exam.
Yes.
So if we find an answer of 3.9, for example, but if we were to put 4, would we get marked down?
For the exam, I would say just do it exactly how it should be. I'll double check to see. There may be with this Canvas software, there may be a range. So I think I can set the margin so that you're close. Because yeah, I mean, you would, for exam purposes and real purposes, I mean, in real life, we're not going to give 3.9 cc's of something. You're going to get 4 cc's. So, but try to be as accurate as possible. And I think I can go through and double check them. And then, if you put the decimal place in the wrong point, or, if I can figure out what you meant, you should be fine. Does that make sense?
Yes, thank you.
Okay. So the other thing we're going to do is dilutions. So that's beginning with a solution of higher concentration and ending a lower concentration. This you may or may not have done. I never did this as an ICU nurse. Pharmacy always did it for us. But once I hit Serenity School, it is very handy to do, very quick to be able to do. And again, some places have these bags, ready to made in the fridge in the pharmacy. Some don't. But being able to figure out how to make your own drips and everything is only going to benefit you. So it's 3 steps. You want to calculate the amount of desired substance. You want to calculate the volume of the starting substance, and then calculate the difference in volume that is to be replaced by the diluent. So our example here, if you have a vial of 2% lidocaine in a bag of 0.9% sodium chloride, how do you make a 50 ml bag of 0.5% lidocaine? So first step is calculate the amount of desired substance. You want a 50 milliliter bag of 0.5% lidocaine. We remember from earlier slides that 5% lidocaine is 5 milligrams per ml. And then 50 ml bag is 250 milligrams. So we want 250 milligrams. And then calculate the volume of the starting substance. So 250 milligrams divided by 20. If we remember, 2% lidocaine is just another way of saying 20 milligrams per ml. So that gives us our starting substance is 12.5, which is close, but we want to be able to calculate the difference in volume that needs to be replaced. So that we want to end up with 50 ml bag, and then you subtract 50 from this number, and that gives us 37.5.
So, how did you get the 250 in the second bullet point? Like, we just take the answer of the first one every time?
Yeah. So you want to find out. So we're looking to make a 50 milliliter bag of 0.5% lidocaine. So 0.5% lidocaine is 5 milligrams per ml.
Mm-hmm.
And so multiplied by 50 is 250 milligrams.
And then do we always take the answer of that one and then use it for the second
step? Yeah. So this is your desired dose. Another way it's that this is your dose on hand. The dose on hand is 2% lidocaine.
Okay.
And then you want to subtract, you calculate the difference in volume that's to be replaced by the diluent.
So
This might be.
Go ahead.
Yeah.
Sorry. This might be a dumb question, but for the third step, the volume being replaced by the diluent. So in theory, it'd be 12.5 mLs of the lidocaine solution, and then we do like 37.5 mLs of saline.
Of saline, yeah, correct.
Okay, thank you.
So you have the desired substance, which is 250 milligrams, and then you add it to starting substance. Is that what the 20 milligrams per ml is?
Correct. Yep. So that's your dose on hand. Yes.
Dose on hand. Okay. Of the vial of lidocaine.
Of the vial. Yeah.
Okay.
So this would, if this was clinical, you'd have a 50 cc bag, and then want to add it in.
So I guess I'm just confused how we're looking. We like did the math to find the desired substance. So how does the desired substance come into our starting substance?
Starting, yeah. So you need basically, sorry, can you repeat that question?
Like we did the calculations to get our desired substance, which
Yeah.
is 50 milligrams. So if that's desired, we don't already have it. So how is that the starting substance? Like I just don't really understand how the 250 is being placed in the second step and divided by 20.
Okay. Yeah. So you're diluting it down. So what you want to end up with is the 50 ml bag of 0.5% lidocaine. So you're going to add a certain amount of 2% lidocaine into the 50 ml bag to get 5% or to get 0.5% lidocaine. So in practice, what you actually have is a 50 cc bag, and then you need to know how much 2% lidocaine you're going to add to that to get your concentration, which is 12.5 cc's.
Okay.
So to clarify, we have the 2%, but we need the 0.5% for the drip.
Correct.
Okay, thank you.
So you're adding the 2% to the 50 milliliter bag to get it down to a concentration of 0.5%. I can, the next couple are a little more practical. If you want me to move to those, then we can circle back to this if that would make it easier.
Yeah, that'd be great.
You want to try that? So this is just hopefully a little more, I know it's kind of, it's hard to visualize when you don't actually do it, but like these are actual like concentrations that you will use and that you will do. So if you have a 50 milligram per, excuse me, if you have a 50 milligram per ml vial of ephedrine, so a big ephedrine here, and you want to dilute it down to 5 milligrams per ml for like hypotension treatment, how many total cc's are in your syringe? So given 50 milligrams is a huge dose, we want to dilute it down a little bit into a smaller dose so we can give smaller aliquots at a time. So how are we going to do that? So what we want is 5 milligrams per ml, which is 5 milligrams. And then we have 50 milligrams total. So we have our desired dose here. Our dose on hand here is 50. And then so that's going to come down to, we want 10 mLs total of solution. And then we have to subtract that from our 1 cc. So we're going to add 9 cc's of saline to your vial of ephedrine. Does that make any more sense? So I'll tell you what I'll do clinically is I'll take a 10 cc flush, I'll squirt out 1 cc, and then I'll drop this vial of ephedrine, which would dilute it down, which is putting, kind of thinking about it backwards, putting 1 ml of 50 milligram per ml ephedrine into a 10 cc syringe here, or 1 ml into a 9 cc syringe of saline, which makes it 10 cc's, which lowers my concentration to 5 milligrams per ml.
Maybe my question is, on the last question, we subtracted 12.5 from the 50 cc bag.
Yeah.
This one, we have 10 ml as an answer, but we're only subtracting 1.
Yeah, because this is, the dose of this is, there's only 1 cc in here.
Okay.
So going back to here, you have a 50 milliliter bag, 0.5% lidocaine. And then when you do it out, it says that's the volume of the starting substance you want. So we want 12.5. We have 12.5 mLs. We have to take that out of the bag, and then that'll give you the difference in the volume. The difference in the volume is to be replaced by the diluent. So this is this 12.5 is your diluent, like the 1 cc is your diluent.
Okay, thank you.
I might be jumping the gun, but some of this is just like a little bit new, and maybe I'm just not quite wrapping my head around it. But are you going to be giving us like any practice problems or anything to work on until the exam?
I can look into that. I can send out a sheet. Would that be helpful?
Yes.
Yeah, practice problems.
So I
I
feel
was
like
looking.
oh, go ahead.
No, go ahead.
I feel like I'm not wrapping my head around this in the slightest. So I feel like where's the 5 ml coming from in the second step? Like I just don't really know where some of these numbers are coming from.
Yeah. So this, your 5 milligrams per ml is your final concentration you want to dilute it down to. And then your 50 milligrams per ml is what it comes in. So it's the same at like 5 milligrams desired dose divided by 50.
So, but when you put it in the second step, the 5 milligrams divided by the 5 ml, isn't it a 50 milligram per 1 ml vial? So where's the 5 coming from?
That's going to come out here. Okay. Yeah. So first, I think it's from up here. 50 milligrams of ephedrine, you want to dilute it down to 5. So you basically, this is what you want your concentration to be, and then this is your 50 milligrams from up here. This are you talking about this 50 milligrams?
I'm talking about the 5 milliliters.
The 5 milliliters. Okay.
Because if the bag or the vial is 50 milligrams per 1 ml, I don't know if we went from that to a 5.
I may have that may be an error actually. Let me look at the other one now. So 50 milligrams.
So in the first problem, the second step had 250
Yeah,
milligrams divided by the 12 milligrams per ml.
Yeah. So I'm thinking I may have just mistranslated here. I think this should be 5 milligrams instead of milliliters. And then that would give you your 10 mLs.
So it should be the 5 milligrams per ml. Because then the
Yeah.
milligrams will cancel out and
Yeah.
you'd be left with the 10 mLs.
Right. Let's go back to the other one here real quick. Yeah. The volume of the starting substance is 20 milligrams because it's 2% for the lidocaine. Yes, good, sharp eyes. So that should be milligrams. So you have 5, you want 5 milligrams per ml. You have 50 milligrams per divided by this number, which is down here, which gives you 10 milliliters.
Okay.
And then you're looking for, it's kind of a reverse problem. You're looking for what you want to add to your 1 cc to make it 10 milliliters. So you're trying to get this number. You want to know how much to add to make that number. Kind of like here, you have this number. You want to know how much to add, or to add basically to make it that number, which is 37 mLs. You want to try and look at the next one to see if that another one makes it. If another one's a concentration.
Yeah. I guess another thing is it like this stuff, the dilutions, it wasn't necessarily in the book that
Yes,
we read.
true.
So I guess maybe
this
that's
I
why
added
it's-
in. Yeah.
Okay, gotcha.
Yeah. Extra points for reading the book. But yeah, this I added in. And this was, I was looking back in my lectures when I went through a course similar to this. And this is part of it. And I remember struggling with it as well. So it does take a little bit of just practicing. And once you figure it out, it does make a little more sense. And once you do a little more repetitions, it will make a little more sense. And I would say even like, I have students come and try to make bags clinically, and they still struggle to try and figure out the math So you'll learn shortcuts too and ways to figure it out. So another one you'll do, another pretty common one here is making yourself a little phenylephrine drip. You want to make just small concentrations of it. So if you have 1% phenylephrine, which is basically another way of saying 10 milligrams per ml, and a 250 bag of normal saline, and then what were your concentration in mics per ml be? So we said neo, short for phenylephrine, neosynephrine. 1% is 10 milligrams per ml. And this is kind of another shorthand way of doing it. So this is a little bit different. I apologize. This is a little bit different than these other solutions, but this might be a little faster for you.
I feel like this way makes more sense.
Yeah. And so 10 milligrams, you have 10 milligrams, you want to divide it by 250 mLs because you have a 250 ml bag. And then that'll give you 0.04 milligrams. Again, we make that micrograms just to make it a little easier. So 1,000 micrograms per ml, 1,000 times 0.04 is 4 mics per ml. So I think the problem with the other problems is it's not doing a concentration. It's asking you how much you remove and add, which I think just adds another step to it. But this is basically figuring out, basically you're going to put this whole vial in a 250 cc bag and gently shake it, and then that's going to give you a concentration of 4 mics per ml.
Am I doing the math wrong? I got 40.
I do.
I may have done math. I may have done the math wrong, actually.
So did I.
Because it is actually, you are right, it is 40. Yes, thank you. Because this is 40 mics per ml is a standard concentration, so 40 mics. Sharp eyes. I was testing your math skills. And then this one is right. I know that. But this is just, again, another practical. Some of you in CVICU hopefully will maybe know this, but this was inspired by a discussion board I got on a Facebook page about there was kind of a newer grad CRNA, and he was asking about how you dilute down the Levophed, because we were talking about Levophed versus phenylephrine. Again, not relevant yet, but the idea how to dilute it down is a good thing to know. So you have a Levophed comes in a 4 milligrams per 4 ml, so 1 milligram per ml bag. If you have a 4 milligram per ml vial of Levophed and a 250 cc bag of sodium chloride, what will your concentrations in mics per ml be? So again, you have a 4 milligram divided by 250, and that should be milligrams, but 0.0016 milligrams. And then we want to figure out milligrams and micrograms. So 0.0016 milligrams times 1,000 is 16 mics per ml. The desired dose diluent gives you a concentration. Then you just multiply that. It's hard to tell what 0.0016 milligrams is. So you want to dilute that out into micrograms. So I don't know if it's a confusing thing, but this may be a little less relevant. But the only thing I wanted to add is, this is just from the real world, from my experience, 16 mics per ml is a pretty high dose. When you're in school, you may hear it's easier to give more and harder to take it away. So I just said, well, just practice diluting it down a little bit further. Since this is just what I do in my practice, I like 4 mics per ml of Levophed when I have it. And basically what I do, not testable, but this is just for relevance here. I have my 16 mic per ml bag. I'll take out 2.5 mLs of that and then fill the rest with 7.5% saline, 7.5 cc's of normal saline. So basically, it quarters the dose of the levofed and gives us 4 mics per ml. So again, I won't ask you that on the test, but just a quick little concentration. If you want to dilute things down with saline, like have it, that's an easy way to do it. Take it in a 10 cc syringe, take out 5 cc's, add 5 cc's of saline. And this is just the math of how I did it. 2.5 mLs of the 16 solution, add 7.5. Your total volume is 10 mLs. And then to calculate the final concentration, you just do it like that. So hopefully I know how many of y'all were feeling in the first questions, but once you figure it out, it'll make sense. Before we go on to anything else, do we want to go back and check out the math, or do we want to just push through?
I feel like
Maybe we could push through and then have a practice sheet to work
Yeah,
on.
yeah, and that's I can make up some practice problems and try
Do you
and
guys
send it
like
out.
that idea?
Does that sound?
that's kind of what I was gonna say, because I feel like I've looked at
Yeah.
these.
Yeah,
in my
it's
first.
right.
Thank you.
I gotcha. So we can kind of shift gears here to temperature. Book talks about absolute zero in the Kelvin scale. Kelvin is named after this dapper gentleman over here. This is the river going through downtown Glasgow, which is a super cool area. This kind of big old spired building is the University of Glasgow, which is like a cool Hogwartsy style castle university. So absolute zero is the coldest possible temperature. There's no temperature lower than zero. There's no negative. It's not 0 degrees Kelvin. It's simply 0 kelvins. So it's an easy calculation on the Celsius temperature scale. 0 Kelvin is negative 273.15 Celsius. So your pretty simple solution here is Kelvin equals Celsius plus 273.15. Just for a reference, absolute zero in freedom units is negative 459.
Question. I've always used 273 for my Kelvin, so if I just use 273 on the exam, is that fine or?
Yeah, that's perfect. Yep.
Okay, thanks.
Then we can move on to density. It's the ratio of the mass of an object to its volume. Chemists usually abbreviate D, while physicists sometimes use rho or P. Either way, it's mass over volume. So density will always have 2 units. Excuse me. It always have 2 units. It always has to have a mass. It always has to have a volume. Like water has a density of 1.0 grams per ml. So density can have a different combination of units. So water also has 1,000 kilograms per meters cubed, and then 8.33 pounds per gallon. So still mass over volume, mass over volume, mass over volume. The other thing is specific gravity, which is the ratio between an object's density and the density of water. And again, it's a ratio, so there are no units. 1 ml has a mass of 1 gram. Specific gravity is equal to the mass in grams of 1 ml of any substance. So materials more dense than water have a specific gravity greater than 1. If they're less dense, they have a specific gravity less than 1. So the clinical correlation here, if you've ever seen a urine specific gravity, it depends on where we're at here. Hopefully you all sitting at home are drinking plenty of water and you're hydrated. If you're having a busy day in the OR and don't have time to drink any water, then your urine specific gravity may go up. So density and specific gravity, it's dimensionless, so it does not depend on units. Specific gravity will always have the same numerical value regardless of the units of density you choose to employ. Any any sample with a specific gravity greater than 1 is denser than water, so it'll sink. Any sample that has specific gravity less than 1 is less dense than water, so it'll float. So if you ever done the experiment where you take, lead pellets and put them in a graduated cylinder, they'll sink. They're more dense than water. If you have something like oil, it's going to float to the top and not separate, so less dense than water. Again, this is just a funny thing for Monty Python. Recommended. Hopefully, everyone's seen the Monty Python and the Holy Grail. And then, so that also leads to baricity, which the ratio of density of a solution to the density of another solution. So specific gravity has to do with water. Baricity is in relationship to another. So a hyperbaric solution, again, don't memorize, it's in the name. The solution is more dense than the reference solution. Hypertension. Hypobaric, the solution is less dense than the reference solution. And then isobaric, the solution is the same density as the reference solution. So baricity has to do with density compared to solution. Does that factor into anesthesia? Oh, good question. So in our case, it comes to play during spinal anesthesia. Sometimes you'll see it as interthecal, and the baricity versus the CSF, so cerebral spinal fluid. If it's hyperbaric, the solution settles in the CSF. As you can see here, it kind of sinks down. If it's hypobaric, it kind of floats up, and then isobaric, it remains near the same. So if you're doing a spinal, you can use different solutions and different concentrations based on positioning. Most are hypobaric, some are isobaric. If you're doing like a C-section, you can give a hyperbaric solution of interthecal in your CSF, and then it numbs the bottom half. So we are a little bit short on time. So I would say that's the end of the first chapter. Give me about 5 minutes just to flip over to chapter 2 and get the PowerPoints up and running. And then we'll start chapter 2. Does anyone have any questions about chapter 1 before we move on to chapter 2? We'll take a 5-minute break and then we'll switch slides, then come back. Oh, wait a minute, should be pulled up. Oh. All right, everybody, let's get back to it for the next chapter, which is Schubert and Lebdia, chapter 2.
Doctor, I have a quick question.
Yes.
I have some practice problems, like some drug calculation and dilution problems that I was using to study for interviews. Can I send it to you before I send it out to the group to make sure it's exactly what you want to?
Yeah, absolutely.
Thank you.
I'm sure that'll be a good help, for everybody too. So, thank you, Lord. All right, can everybody see the slideshow?
Yep.
Okay. So our next chapter is chapter 2. So just some chemistry basics. Why does it matter from the bedside to you? The clinical scenario they gave is a 56-year-old patient who with a diagnosis of hyperparathyroidism is brought to the OR for a parathyroidectomy. Interop, the PTH hormone and ionized calcium levels are obtained prior to the removal, and then after the removal, usually about 7 or 8 minutes afterwards. It shows the need for IV calcium, so you give 200 milligrams of calcium. 15 minutes later, a calcium level shows a small increase from 6.2 to 6.8. So you drop some calcium chloride, and then you draw it up again. You say, oh, my vial was calcium gluconate. So is that an issue? Do you need more or less calcium sulfate? So what's the difference? We will get into that. The point isn't to answer this specific question, but just to have an understanding of calcium chloride versus calcium gluconate. Same thing, Schubert and Lebdia. So in this lecture, again, it'll be a pretty broad overview of everything. Hopefully, you've come across some of this in your chemistry already. If not, it'll be a good review for you. Just a review of chemistry, atomic structure and dimensions, Dalton's atomic theory, the periodic table, some nomenclature, electrolytes, and then some light stoichiometry. Again, we're looking at this from a nurse anesthetist perspective. I'll be the first to admit to you, I'm not a chemistry genius. I don't have a PhD in chemistry. My doctorate is in nursing. I'm a practicing CRNA. And when I talked to Dr. Rawson, she said she wanted just a basic overview from the practicing provider's perspective. So this is your 10,000 foot view here. This picture is actually of Albuquerque. I also teach a little bit or make lectures for New Mexico State in Las Cruces, New Mexico. So some of the pictures are recycled. I like this because I'm very much a 10,000 foot view guy and then zoom into the smaller perspective. So you can take if you're ever in Albuquerque, this is Sandia Peak. You can take a tram up to the top. It's super, super cool, kind of a terrifying tram ride. But once you get up there, I think there's a ski resort and a cool view of everything. But so what is chemistry? It's the study of matter and changes it undergoes, including matter, physical, and chemical properties of pure substances and mixtures. So matter is formally defined as anything that has mass and occupies space. It doesn't have to be visible. For example, air, nitrous oxide are all matter. Light is not matter. And then atoms are the basic building blocks of matter. So under ordinary conditions of temperature and pressure, essentially all material is comprised of atoms. Atoms sometimes join to form molecules. An element contains only a single kind of atom, whereas compounds contain 2 or more kinds of atoms. So we can zoom down a little bit. They're further made up of protons, which, as a reminder, have a positive charge and a mass of 1 AMU. Neutrons, they're electrically neutral and have a mass of 1 AMU. And then electrons are negative charge and have a mass so small it doesn't contribute. So a couple more terms. Elements, they're comprised of 1 or more kind of atom. Compounds are comprised of more than an atom ratio mass. And molecules, you might say as molecular compounds, are a group of atoms chemically bonded together in a discrete unit by covalent bonds. Molecules are electrically neutral. And then we can further down a little more. Ionic compounds contain positively charged ions and negatively charged ions. There's no discrete units of an ionic compounds that are neutral. All positively charged ions are attracted to all the negatively charged ions versa. So our definite ionic compounds are not molecules. That matter can't be created or destroyed. It can only change forms. Physical and chemical. The neighborhood boy is running around outside the window. So there are 2 categories of change: physical and chemical. Physical changes occur without changing the chemical makeup of the substance. Water, that's the physical change. It's still water, just in a different form. It's integral to the material regardless of how much material is there. And then extensive properties depend on the size of the sample. And then the chemical change always results in the formation of a chemically different substance. Like think about breaking down water into hydrogen and oxygen. So physical changes, it just changes shape. Chemical changes, there's still hydrogen and oxygen. Nothing's created or destroyed. It just comes in different forms. And then pure substances and mixtures. Pure substances are materials that cannot be physically separated into simpler components. The chemical and physical properties of a substance are uniform through all the samples. A substance can either be a compound or an element. If the substance is a compound, it can be chemically separated into its elemental components. And so those substances, mixtures, are comprised of 2 or more pure substances. Mixtures can be resolved into simpler components through physical process. Homogeneous mixtures are uniform in chemical and physical properties throughout the sample. Think of like normal saline. And then heterogeneous mixtures exhibit distinct phase boundaries between its components. A phase boundary is a demarcation of where the chemical and physical properties of the sample change. For those of you who read the book, emesis would be one example. Yes, that is from the book, so don't dwell too much on that. But you think about, if I have my glass of water here, there's water, there's other chemicals in it. Emesis would be, there's chunks, there's green, there's bile, there's all kinds of stuff in it, but it's still, there's distinct boundaries. I guess you think like oil and water. The oil is going to float, the water is going to be where it is. This is just another good for those of you that are visual learners. There's a pure substance. It can be a mixture. It can be homogeneous. It can be heterogeneous. There's also compounds and elements. Just a good physical breakdown of everything. So the atomic number, electrons surround the nucleus in a nebulous cloud that is described by quantum mechanical rules. I know in the old days you may think of it like the solar system model, but it's more like this with in a different orbit and probability clouds. And just a reminder, atomic radii are they're 100 picometers, which is 100 times 10 to the minus 12. So very, very small. That leaves us with an atomic number. All atoms contain protons and electrons. Except for hydrogen, all atoms contain neutrons. The atomic number of an atom is the number of protons in the nucleus. The identity of an atom is determined exclusively by the atomic number. So carbon has an atomic number of 6. All carbon atoms have 6 protons, and all atoms that have 6 protons are carbon atoms. The neutron number is the number of neutrons in the nucleus, which is and then the mass number A of an atom is the sum of the atomic number and the neutron number. The unit for atomic mass is the AMU, which is atomic mass unit. 1 AMU is defined to be exactly 1/12 of the mass of 1/12 carbon atom. Protons and neutrons have an atomic mass of about 1. We have with carbon 6 protons, 6 neutrons, electrons, and then an AMU is 12. One second here. I'll be right back. Okay, I am back. Apologies. The neighbor boy was playing in our yard and he was knocking on the door, so I was just making sure he didn't need anything, but he wanted to play with my children who were at school right now. So, all right. So talk about that. So the atomic number. Again, this is not super hardcore chemistry, but for our purposes, it's okay to just say the mass of the proton and neutron are equal, and then you can ignore the mass deficit. I know you can calculate that out, but just for our purposes, we can keep it simple. You can easily tell the atomic number from the mass number because the mass number can never be smaller than the atomic number. The mass number is frequently written as a superscript, and the atomic is the subscript. Sometimes the element name is simply followed by the mass number. So elements are always electrically neutral. Each atom must have an equal number of positive charged protons and negative charged electrons. The number to emphasize the importance of electrical neutrality. Imagine a sample of graphite with a mass of 1 gram. That's about the amount of graphite in a pencil. Carbon is an element number 6, and each carbon atom has 6 protons. If each carbon atom were missing 1 electron, the amount of charge in this quantity of carbon would be about 8,000 coulombs. So that's like 400 times the bolt of lightning. So important to keep things neutral. A pencil, the amount of carbon in a pencil could kill, graphite in a pencil could kill you. So you will come across isotopes. There's radiotopic isotopes. There's mass spectrometry. Again, not as relevant, a little relevant to healthcare, but not as totally relevant. Talking about how is it actually made and how you actually come up with the mass spectrometry information. Basically, how do they determine the mass of an atom? They vaporize a sample under high temperature and low pressure. Then they bombard the vapor with high energy electrons. This pushes the molecule on a curved path, which depends on the mass of the molecular ion. And then they use magnets to manipulate the curve, and then that's how they scan for the atomic mass. So I just find that kind of interesting. So, but it was also interesting because it led to the discovery of isotopes. And just as a reminder, isotopes have the same atomic number, but a different mass number of this. So same Z, different A, or the same number of protons and a different number of neutrons. So an isotope of an element behave almost identically, except that it's heavier and it bonds slightly more stronger. So these are the different isotopes of hydrogen. So different numbers of protons and neutrons. And then so a little heavier, act a little differently. We can move on to Dalton's atomic theory. Elements are composed of tiny, indivisible particles called atoms. All atoms of a given element are identical and unique. Atoms are formed by atoms that are in a fixed ratio. Chemicals do not create, destroy, or change atoms into atoms of other elements. Chemical reaction cause atoms to recombine into a new substance. So if you ever read about like history, there was the study of alchemy, which would be people trying to change lead into gold, which we know is not physically possible. You can't change elements, and mass can't be created or destroyed. Dalton also postulated the law of multiple proportions. Some elements can be combined to give more than one compound. So like nitrogen and oxygen, they can give us several stuff, including nitrous oxide, nitrogen dioxide, which is pollution, versus nitrous oxide, which is what you will use in your anesthesia practice. And the ratio of the weights of the elements in these compounds is always a ratio of small whole numbers, which supports the notion that the elements must be delivered as particles rather than a continuous substance. So as you can tell by Dalton's picture or his painting, a lot of his original theory has been modified, but it does provide a good working foundation for everything that you will do. And this is a very old anesthesia machine. So you can move on to the periodic table. Again,
Are you muted?
oh, can you not hear me? Can you not hear me?
It's
better
better.
now.
It is.
Oh, okay. Do I need to go back or what? Where did I cut out?
Right about here, the periodic
Okay.
table.
Okay. So this is just the Russian chemist Dmitry Mendeleev. He credited with organizing the first table in 1871. This is him on the left here, and I just thought he kind of looked like Dumbledore. My third grader, almost fourth grader, is a huge Harry Potter fan, so she really liked this picture. So I'm sure you'll have seen it in every science classroom in existence, but it's organized according to the periodic repetition of chemicals and physical properties. Elements are listed in order of increasing atomic number, so each successive element has one additional proton. The vertical columns are groups or families. Elements in a given group have similar chemical and physical properties. So you can see hydrogens are here, alkali metals, alkali earth metals, transition metals, etc. And Here we're going element that says 1 additional proton, so helium 2. Each row on the periodic table is called a period. The first period contains hydrogen and helium. And then your second one contains lithium to neon. Each successive element has 1 additional proton. Each successive element also has 1 additional electron, which makes sense since they are electrically neutral. The atomic weight listed on the periodic table are the weighted averages of all the atomic masses of the natural occurring isotopes of that element. That's here. I chose xenon as a fun aside, and that once you learn about anesthetic gases, xenon would actually make a very good anesthetic gas, but it's difficult to manufacture and costly to manufacture. So let's talk about classifying elements with our periodic table. Metals are the first one. Their most common element on the table. It's the left side of the table. They have a shiny luster. They're ductile, so they'll be able to be drawn into wires. They're malleable, able to be beaten into thin sheets. If you drink in a can of soda, you know that. They're a good conductor of heat and electricity, and they react chemically to form cations by giving away electrons. And then nonmetals, the right side of the periodic table, they're in the dark blue boxes. They can be solids, liquids, or gases. The solid nonmetals tend to be brittle, with the exception of carbon in the form of graphite. They do not conduct electricity. If they form ions, nonmetals tend to form anions. We'll get into that, why that is in a little bit. The other one is metalloids, semi-metals, sometimes they're called. They have properties intermediate between the metals and nonmetals. Metalloids have a shiny luster, but they're less malleable and ductile than metals. They conduct electricity, but not nearly as well as metals. They're also called semiconductors. Silicon is the most known of the semi-metals because it's used for constructing semiconductor computer chips. So if you have an iPhone or a smartphone, it's most likely have some sort of silicone in it. I am here for a 5-minute break. We're about halfway done, so we can take a break or keep the rope. Is anyone any strong feelings either way?
Can we keep pushing through and just
Yeah, I bet we push.
Yeah.
with it?
So the rules for naming chemical compounds depend on whether the substance is a molecular substance or an ionic substance. Molecular compounds are comprised of nonmetals. Ionic compounds are almost always comprised of metals and nonmetal. If a compound contains the polyatomic ions listed, it is an ionic compound. Again, don't memorize this list. This is just for reference for you. So molecular compounds are easier to name than ionic compounds. Molecular formula of a substance gives the number of each kind of atom in the molecule. So to name it, you name each element, indicate how many of each element are present with a prefix number. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, and octa is 8. And then you add the suffix "I" to the last element. So N2O, dinitrogen monoxide, also nitrous oxide, or NO, nitrogen monoxide, nitrous oxide. Something like P2O5 would be diphosphorus pentoxide, silicon dioxide. So these are, I think, just the Greek prefixes. So those are pretty easy to name the molecular compounds. What about ions and ionic compounds? So an ion is an atom or groups of atoms with a charge. Reminder, cations are positive. anions are negatively charged. Ionic compounds consist of ions and they're held together by ionic bonds or the attraction of the oppositely charged ions. I'll get into that a little bit later too. In the solid state, ionic compounds form crystalline lattices in which all the cations are attracted to all the neighboring anions and vice versa. Since you can't identify any anion that is associated with any particular cation, there are no discrete ionic molecules. So in other words, a compound. Ionic compounds are sometimes referred to as salts. It's not totally true, but just for now, we can consider all ionic compounds salts. And this is just in everyday life: table salt, baking soda, drain cleaner, bleach. Those are all ionic compounds. Another question? No, it's another question. I heard a ding. Oh, I think somebody logged out, came back in. Okay. Someone logged out and then they come back in. So representative metals almost always form cations in which the ionic charge equals the group number. Since the group number is equal to the number of electrons in the highest energy level, partially filled electron shell, by giving these electrons away, a representative metal is able to obtain an electron configuration that is identical to the closest noble gas. I will have a periodic table in the next slide to have a visual example here. All the metals in group 1A form cations with a charge of +1. All the metals in group 2A form cations with a charge of +2. Aluminum forms a cation with a charge of +3. To name a representative cation, name the element and add cation or simply ion. There are no simple cations with charges of 4+. So I know that's a lot, but we'll look at that. So one of the noble gases, because that's the most stable. Group 1A over here. Sodium is in group 1A and forms a cation with a charge of +1. Sodium metal has 11 electrons, and one of these electrons is in the third electron shell all by itself. By giving away that electron, the resulting sodium cation has the exact number of electrons as neon, and all of its electrons are filled. So we can look at over here. It can give away electrons. It's got this one extra electron. It can give it away. It becomes like neon, and then it is stable. And all its electron shells are filled. And then normally it can bond with, it can take chloride is missing one, so they work together. For anions of representative elements, the ionic charge is based on the number of electrons that nonmetal needs to gain in order to have as many electrons as the nearest noble gas. So oxygen is 2 boxes away from neon, the nearest noble gas. Therefore, when forming an anion, oxygen will require 2 electrons to gain a charge of -2. Nitrogen forms an anion with a charge of -3, while fluorine forms an anion with a charge of -1. So to name the monoatomic ions, add the suffix "I" to the stem name. So chlorine, Cl is chloride ion, sulfur is sulfide, phosphorus is phosphide. And then more transition metals. Most transition metals form more than one cation. Iron can form Fe2+, Fe3+. So it's not easy to predict the charges on the cations that transition metals are likely to form. The most beginning students usually wind up memorizing the list. Don't memorize it, but it's here if you need it. A few examples of some common transition metal cations are given in the following. If the transition metal forms one cation, you name it like a representative metal cation. So name the element and call it a cation. If the transition metal forms more than one cation, you need to name the metal and then indicate the charge on the cation with the Roman numerals in parentheses. So Fe3+, iron Fe3 cation. SN2 plus is tin 2 cation. So you can kind of see it. Iron 2 and 3, copper 1 and 2, Cu copper 1, or Cu copper 2. There is an older system for naming transition metals. You name the lower charge ion as the OUS ion, and then the higher charge is the IC ion. This is in the Roman system, but so it's less common in academic use, but still a little bit common in medical settings. So chromium would be chromius, Cr2, Cr3 would be chromic ion. This is pictures if there's any Latin or Latin nerds out there. This is the textbook that you probably use to learn it. I took Latin my senior year of high school, and it was a huge mistake because it's a crazy language. But it's helped me a little bit in chemistry and stuff. So if the chemical symbol is based on the Latin or Greek name of the element, so that would be, you could tell the chemical symbol isn't the first two letters of the element's name, so kind of the older ones. Use the Latin or Greek stem name. So Fe is ferrous, Fe3 plus is ferric, and then the clinical example of this would be if anyone's taken iron supplements, ferrous sulfate, FeSO4 for common iron deficiency anemia. And then it's ferrous because it's Fe2 plus. I know this is a lot, but we'll get through it. Polyatomic ions, they're formed by two or more nonmetal atoms bonded together in a way that result in a net electrical charge. Some of these ions merit special comments. SeO4, 2 negative, SO3, 2 negative, differ only a single oxygen atom. But in these cases, the ion with the larger number of the oxygen atoms is given the 8 suffix, while the ion with the smaller number of oxygen is given the ite suffix. So we can look at like carbonates, hydrogen sulfide, sulfite, sulfate. Again, this isn't a chemistry class. Well, it is, but it's not a chemistry major. You're not chemistry majors, so don't memorize the polyatomic ions. Don't memorize any of these. Don't memorize the chart. Just be familiar with some of them. So again, a clinical correlation here. Sodium bicarb. HCO3 contains hydrogen atom. They are formed by combining with the parent item. So these acid salts can be named in two ways. Systemic ways simply say both components. So it's formed hydrogen plus a carbonate. So it's hydrogen carbonate. The more common name is bicarbonate. Just for a clinical connection. So if someone says, "Oh, he needs an amp of bicarb," you can say, "Oh, it's actually hydrogen carbonate." You'll sound very smart, and your preceptor will love you. So formulas and ionic compounds, as we talked about, atoms must be electrically neutral, so the net charge must be 0. When a metal gives its electron away, there has to be another chemical, usually non-metal, to accept them. There are no ionic molecules because every cation is attracted to every anion. So there are no identifiable ion pairs that belong exclusively to each other. So the formula of an ionic compound is an empirical formula. It lists the simplest ratio of cations to anions necessary to achieve electronic neutrality. So when you're forming an ionic compound, the total positive charge contributed by the cations must be equal and opposite to the total negative charge contributed by the anions. So for ion pairs with equal but opposite charges, the ratio is usually 1-to-1. But again, that's not always the case. So we'll look at what happens when ionic charges aren't equal to each other. So there's a most mathematically sophisticated way to determine this ratio is to seek the least common multiple between the absolute values of the charges on a cation and an anion. But again, this is CRNA school, not chemistry school. So we will use what's called the crisscross method. So the number of cations in the formula is the absolute value of the charge on the anion. The number of anions on the formula is the absolute value of the charge on the cation. So we can see here, we can crisscross AlO3, and we can crisscross, so it's going to be Al2O3. So some more examples: sodium CO2-3, you're going to crisscross Na2CO3. So we'll expand upon that and write that out a little bit. This is just a quick little guide how you want to do it. So step 1, write the symbols and charges. So identify the cation, which is positive, and the anion, which is negative, and then write their symbols along with their charges. So we have magnesium chloride. Magnesium is 2+, chloride is minus. So then we crisscross them. Mg2, and then Cl minus. So you take the absolute value of each ion's charge and use it as a subscript. So the charge on Mg2 becomes the subscript for Cl. The charge on Cl becomes the subscript for Mg. That gives us Mg1Cl2. You don't have to write the 1, so it's MgCl. And then you can simplify if you need it. So if it's if it would be 4 and 6, you can bring it down to smaller numbers. If the subscripts can be reduced, the small whole number do so. So it's already in it. But if the ion, if it was like Fe3O2 after crisscrossing, you would want to bring it down. So it's not Fe3O2. That makes sense. Sorry. I don't know why that's on there, but so if you get like 4 and 6, you can bring it down so it's the smallest number possible. And write the final formula. Ensure the compound is neutral. Write the elements in the correct order. Remember, it's cation first, anion second. Give you another example that hopefully is a little less confusing for you. So aluminum sulfide, Al3+, sulfide is -2. Again, I don't want you to memorize the charges on the test because it's irrelevant to us. So if on the test, you'll have the charges. You don't have to look up the charges or anything. So you can do the crisscross method. Aluminum gets a subscript of -2. Silicon gets a subscript of 3. So Al2S3, and then simplify if needed, but it's already in the lowest number. Clear as mud?
Yep.
So we've created the element. So let's give our compound a name. Just name the cation and then the anion. But first determine if it's an ionic compound or molecular. So if it's in a molecular compound, you must include a prefix, multipliers, di, tri, the ones we talked about, to indicate the number of each kind of atom in the molecule. In ionic compounds, you must not include a prefix multiplier because the number of each ion in the formula unit is controlled by the charges of the ion. So potassium sulfate, K2SO4, sodium oxide, iron sulfate, Fe2SO4, iron 3 sulfate or ferric sulfate. If the cation is a representative element, it's not necessary to indicate the charge because these metals form cations with an ionic charge equal to the group number. When naming ionic compounds that contain transition cations, you need to indicate the charge on the cation, either by including the Roman numerals to indicate the charge or by using the ic, OUS sulfites suffixes. So how do you determine if the charge on the cation, how do you determine the charge of the cation from the formula? You have to learn the charges on the anions and assign a charge to the cation so the formula achieves electrical neutrality. So the example here, iron sulfate contains an iron cation and a sulfate anion. Since the sulfate anion has a charge of -2, the iron must have a charge of +2. That's be neutral. So FeSO4, it's got to be 2. And then contain Fe2SO4 contains 3 sulfate anions. Since each sulfate carries a -2 charge, there are a total of 6 negative charges contributed by the sulfate anions. So there has to be 6 positive charges between the 2 cations. So iron cations must be 3+, and Fe2SO4 is iron 3 sulfate. It's got to be balanced. The things we'll come across are hydrates. Some ionic compounds have water molecules in their formula unit. The compound that contains the water is called the hydrate, and removal of the water affords the anhydrous salt. So don't memorize it's in the name. Without without hydrogen. Compounds that have strong tendency to absorb water are called hygroscopic. And to name the hydrate, you simply name the ions and then add the appendage hydrate along with a multiplier to indicate the number of water molecules in the formula. But naming hydrates only makes sense when you're dealing with solid substances, because when a hydrate is dissolved in water, both the ions and waters of the hydration separate in a mix uniformly with the water. So a real life example of this, the anhydrous form of a compound that has a strong tendency to absorb water can be used as a desiccant. Desiccants scavenge the last traces of water from a system. If anyone's ever opened anything and there's a silical gel, it says throw away, do not eat it. So silicone, you add it adds water to it. It's a reversible process. So hydrated forms of a desiccant can be used as moisturizers. So how does that apply to anesthesia? Oh, good question. Soda lime. If you've ever seen an anesthesia machine, there's a absorber below it that is this lovely white shade, and then as it gets used more and more, it turns beautiful little purple. Again, don't memorize this formula. This is just trying to connect it to your practice as future CRNAs. So carbon dioxide, hydrogen makes our formula here. The first step is a neutralization reaction, and then there's a second neutralization reaction. So not for you to memorize, not for you to write out the formula, just to know that this is where desiccants are in your practice, and that's why it's on here. So we can move on to electrolytes. Again, something you'll see in experience. Something you've seen in experience as a nurse, and I'm sure will come to you. So electricity is generally described as the flow of charged particles under the influence of an electrical field. So this will come into play too when you're learning about anatomy and physiology, about electron conductions and signal conductions. We can't have an electric current in a system unless there are charged particles that are free to move around. An electrolyte is a substance that dissolves into water to give a solution that conducts electricity. A non-electrolyte is a substance that dissolves in water to give the solution that does not conduct electricity. So again, electrolyte conducts electricity. Non-electrolyte does not conduct electricity. While most ionic compounds are only sparingly soluble in water, those few ionic compounds that readily dissolve in water are electrolytes. Molecular compounds are non-electrolytes unless they have acid or base properties. So when an ionic compound dissolves in water, They mostly separate into ions that freely and independently move around in the solution. Since these ions are free to move around in the solution conducts electricity. We can move on to stoichiometry. We'll get more into electrolytes later. That comes in. I think that's its own chapter. So what is stoichiometry? They're calculations that relate to the amount of reactants and products in a chemical reaction. So again, it's not as detailed as what you learned. Is probably what you learned in undergrad, but we can just review the basics. So we talked about a mole. It's the amount of substance that contains exactly as many particles as there are in 12 grams of carbon. Particles mean molecules, atoms, ions, and electrons. So that leads us to Avogadro's number. Said Avogadro's number, 6.02 times 10 to the 23rd, which is a simple way to convert between particles and moles. Which also leads to molar mass or molecular weight. It's an element, molar mass, grams per mole, is an element of an element is equal to its atomic mass. For molecules, the molar mass is equal to the sum of the masses of the component atoms. So you can use the words interchangeably. And that is the end of the lecture. Does anyone have any questions? We have a couple of minutes so we can go over stuff.
Is 1 mole Avogadro's number?
Yes. So that's yeah. It's a good way of saying it.
What time are exam reviews on Tuesdays?
That is up to you guys. It's probably, let me look at my calendar here. I think the first one's gonna have to be in the evening because I think I work that day. Let me pull up my chart here. I'm referring to my calendar here. So y'all's first test would be the 5th of June. Yeah, and I'm working, yeah, so it'll be in the evening on the 3rd. Is there a time that works best for everybody?
I think quite a few people that I know there's some new moms and have families, so I feel like logically it might be best to do things during the day. That way people can unwind with their families in the evening and spend time with them. I don't have any kids or anything like that, but that popped in my head.
I'm okay with what works.
And again, it is optional too, so it's not if you can make it, you can. If you can't, that's perfectly fine. It's not a big deal. It's more of a like kind of reviewing concepts that you're struggling with, not here's what's on the test.
After 5:30 works for me.
Okay.
I'm one of those new moms that Lauren mentioned. If there's a chance that we can't make it, because like 7 to 8's the witching hour, if you know, you know.
Oh yeah.
So would these be recorded?
Yeah.
To be reviewed? Okay.
Yeah.
Cool. And then I have one more question.
The 5 o'clock fussies.
Yeah. If the practice problems at the end of the chapters in the books, are those pretty similar to how this material is going to be tested on the exam?
Yeah, that would certainly be a good way to review.
Okay, thank you.
Obviously, this is a lot of information to review in one sitting. Is there a good way to do more like application of these concepts since most of our grade is just the test?
Yeah. What do you mean by that?
A lot of our like content in the modules is just like PowerPoints and things like that, besides like the questions in the back of the book, are there other resources that you recommend to help kind of make these concepts
Yeah, kind
click?
of. Not really. I mean, for this class and for the test, the book is probably the best resource. There's other resources out there, but those are probably going to be a little more detailed than what you need for everything. I know like Khan Academy is a good resource for videos, and if you're looking for a little more information, but the disadvantage of that is it's going to be a little more in detail than what you need. Because those are for more.
So, obviously, I'm going to read the book on top of like doing the lectures, but are the lectures the main information that we should really focus on?
Yeah, I'd focus on the lectures and the PowerPoints.
Okay.
Because I know some of the stuff, like the drug stuff, I liked from old lectures, so I've added it in.
Okay.
Know everything.
What kind of questions are going to be on the test? Or what kind of a test are we looking at?
So I'm sorry, I don't understand your question. Like, what do you need to like?
I guess like what kind
Like
of like
essay versus multiple
questions?
choice, or
Yeah, and is it like what kind of a problem would we be like looking at?
most likely the same, just from the notes. The chemistry stuff will just be like chemistry related questions. The math, I need to figure out on the Canvas what I can physically do and not do. I would like to have some math calculations on as well, some simple calculations. And like I said, if it's like a weight-based dose, or I want you to calculate something, I'll give you the weight, I'll give you the dosing and everything, so you don't have to memorize it. So a combination of multiple choice, should be some no essay questions, but mostly multiple choice and then some calculation questions. Does that answer your question?
Yes, thank you.
Oh, Mary says, I'm struggling to determine what information necessary enough for this class and what's just for. So in terms of what's necessary for the class and what's just for information, I know I add some extra stuff just to kind of connect it to you guys. If it's in the book, you should probably know it for the class, besides the drug calculation stuff. I'll try my best to just kind of annotate, hey, this is just for your own learning and not for the test, but that's good feedback to kind of determine, because I know it is a lot. So, I mean, and I think next chapter is, next test is even more chapters. So there's one, unfortunately, with the condensed schedule, how it breaks out, that it is quite a few slides. So I get it. You're not going to like this answer, but I'm going to say welcome to CRNA school. That's unfortunately how it is. It's a lot. But I know you all are smart, and I know you guys can all figure it out. And I used to hate when people would say that to me as a student, so I get it. Does anyone have any other questions?
Yeah, I guess like it is a lot of information, but like, are we gonna need to like chemical nomenclature? Like, are you gonna be giving us like charges and stuff, and we're gonna have to be like deciphering the names and like putting chemicals like formulas together to create new names? And like, are we gonna need to know the prefixes and et cetera, et cetera?
So I don't really want you to memorize anything, but know the concepts behind it. In sort of like, there's the charts of like the different numbers and stuff. Know that, but not necessarily like, I don't want you to memorize Fe2 minus and stuff, but know the concepts behind it.
Okay.
After each exam, would there be an opportunity to go over what we missed? Just thinking. So Alexa asked, after each exam, would there be an opportunity to go over what we missed? I can certainly look into that. That may be limited by the school's policies in terms of test reviews. So I'd have to consult with Dr. Rawson about that and see if that's one, if it's allowed.
For this class, is there going to be a comprehensive final, or is it just the 4 exams in the group project?
Just the 4 exams in the group project. Yeah, no comprehensive final.
Awesome. Thank you.
So each exam is just over the module. Module 1 exam is just over module 1.
Can we get an idea of like the length of one of the tests? Like
probably 40 to 50 questions.
Okay.
Sorry, I keep harping on this, but this is grad school, but is there going to be, can we expect any, like, maybe study guide's the wrong word, but any practice problems for chapters 1 and 2, or are we just expected to just understand the material and show up?
So I can send out, I can do some math problems or check out the math problems that someone was going to send out, or that she said she used to practice. But other than that, no. You guys are certainly welcome to. Okay, Lauren did already. You guys are certainly welcome to come up with your own study guides and share those among yourselves as a group. If that's what you want to do. But that's all within you all. Can't say y'all because I want to say y'all, but you all. Now I will figure out how to post this. Hopefully, yeah. So if you want to review. Anyone have any other questions? Just as a reminder, please read. It's Schubert and Lebdia, chapter 7, and then the PowerPoints as well prepare for next week. I think I will email you at the time. Like I said, I sent out that survey, Monkey. So if you haven't completed that, please complete it. So far, the results were leaning towards this same time on Thursdays, which is fine. If we want to reevaluate later, come July and August, we certainly can. But morning or afternoon on Thursdays is best for me, just because of my work schedule. And then we can, if we want to change it, we can. But does anyone else have any other questions? I will dismiss class. Okay.
Thank you.
Have a good
Thank
rest of
you
your
so
week.
much.
Congrats on almost finishing
Thank you,
your
you
first
too.
week of CRNA school.
Thank you.
Thanks.